तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Design of memories is one of the challenging areas. We need to take extreme care while designing systems for ASIC as well as FPGA implementations. And so as far as the memories are concerned, there are basically two types, ROM and RAM, and organization of these memories would depend upon the typical applications. And often the conventional memories that we use having either a single address, single output pattern, or dual port RAM, etc., may not be of help for typical applications that we are going to address here. And naturally this calls for tailor-made designs for these applications, and one such application that you see is right here with two address. For example, we call this is a ROM design, and it has dual address and dual data. And what is implied here is, and it is also synchronous, that means to say it is also pipelined, and we need naturally a clock as the one of the inputs, and two addresses are there so that we may fetch two locations. It can be very same location or different locations, but the number of locations that you have is actually decided by the number of bits in the address. Here in this case it is 3 bits here. Therefore, this ROM contains 8 locations totally, and each of these locations is 64 bits in width, and corresponding data that you need to read from the ROM table is dout1 if the address 1 is applied at the inputs. Likewise, for address 2 you need to get data out here, which is also 64 bits in width, and note that the ROM content is only single, and what all you have here inside this 8 into 64 bit organization of ROM, and contents is just one block as such, but the two addresses are involved here. In other words, we need to access two different locations simultaneously. That is the implication here, and this arises in one of the design applications called discrete cosine transform and quantization. This is for used in JPEG, MPEG-1, MPEG-2 video compression, and we will see this design application later. And for that we need this design, and likewise other designs that we are going to consider, such as a single address ROM or dual RAM, dual redundant RAM, etc., which we are going to consider will also be used in the same application. And let us see how the design flows. And here in DCTQ we have what is known as a cosine term, and you need a ROM for storing such cosine values, and that is why the C is put here. And we also need a transpose of the these constants which are put into the ROM, and they are basically cosine terms, and we need to get a transpose of this. It is basically a matrix, say, and we need to get a transpose, and this can be got by changing the address from address 1 to address 2. So you can, if you want C, you just address use only address 1, and use address 2 if you want its transpose, and that is the reason why we have dual address design. And this is note that this is not a conventional approach. So any other design would have only a single address and a single output, either 64 bits or 8 bits and so on. Let us go into the design of this. So this is the comment here, a group comment is put in this fashion, and these are all bulletin here. I will just read out for your understanding. This is the ROM that stores the cosine and C and CT matrices. In fact, what we need is only a C and CT, but for manipulation of scaling the final pixel value, etc., in the DCTQ, we need multiplication by a factor of 2, and that being one time affair, why not we integrate that constant, I mean multiplication also right in this cosine value, and the result is we put a ROM with twice the contents that we really require, because this is what we really need while processing further in DCT quantization. And next point is two-stage pipelining for this C and CT to keep pace with dual RAM used in the DCTQ design. So in this case we have another specialized memory called dual RAM. We will go into the design of this as well later on for use in the same application here, and mentioned here as DCTQ. And in this dual RAM we need to have two-stage pipelining. That means to say the output is delayed by one clock. So whereas in this ROM it would be enough if you just get the output with single pipelining, and in order to keep pace with the dual RAM we need to delay this output of ROM, and that is the reason why we are having two-stage pipelining. And third point is the ROM size is 8 into 64 bits, as I already mentioned, and two locations can be accessed and output to the data bus, DOUT1 and DOUT2 simultaneously. These are all the data bus here, and using the two addresses, address 1 and address 2 respectively. The comment ends here, and the actual code starts here. The Verilog code for the ROM which is to retrieve C and CT matrices is shown here, and we need to declare that design, and we will name it as ROM C. CT is also implied. If you want you can put CT here, it does not really matter. And we need to say module, and finally towards the end there must be an end module as well. And we have already seen that there are three inputs. One is a clock input, other two are address inputs, as you have already seen, and corresponding output that you want to retrieve from the ROM is DOUT1 and DOUT2, both naturally are outputs, and they are 64 bits in width. That is what is shown here, 63 through 0, and as usual MSB is written first and LSB last and separated by a colon. And similarly the input also has its width. Here in this case there are only 8 into 64 bits, so this 8 corresponds to 3 bits here as the address. During the next few lines we will see what this DOUT1 next is. For the time being I will just mention that this is a combinational signal, and therefore but it is coming within an always block, and therefore we need to declare it as reg and not as wire, and only in assign statements you need to use a wire there. So here it once again this is same as the data out 1, these are all intermediate results stored, and it is not really stored, in a way it is stored because we use a reg here and in always block, and this is the next value that will be loaded into dout1 reg1. So as I mentioned, there are two pipeline stages. In the first pipeline stage, when the clock strikes at that is at the positive edge of the clock, this dout reg1 will get the content of dout1 next, and in the next clock pulse, that is the second line of pipeline stage, you will get the final output itself, which is the desired output, that is dout1 and dout2, based upon what address is contained in address 1 and address 2, which we have already seen here, and this we have already covered, and they are all basically registers here, and this one is, although it is a combinational signal, because it is put in the always block, we have to declare it as reg, as we have seen before. And in addition to this, we are also going to use corresponding to 8 locations. We have seen that the memory contains 8 different locations, each of which is 64 bits. So we need to declare those locations as well, and they are named as LOC 0 through LOC 7, and each bit is mentioned here, 63:0, 64 bits, and they are all using assign statements. So we need to declare them as wire here. We have mentioned that this ROM is what we are implementing is only a ROM, and which contains 2 times the cosine matrix as well as or 2 times the transpose of the matrix. Both imply the same contents. So the contents of the ROM is precisely what you see here, and the very first location is here, and the MSB is this one, the 5B here, and total width is 64 bit, and therefore it is declared in this fashion. It is straight away represented in hexadecimal, and we have used assign statements here, and that is the reason why we declared all this LOC as wire here, and so we need to, this is only a combinational logic portion here, and whenever this location changes, only then we need to make the assignment, and while doing the assignment we will use the case, because what all we want to do is read out from one of the locations. Each of the location is 64 bit, which is a ROM content, and depending upon the address that we supply, whether the address is ADDR1 or ADDR2, which is to follow this, and depending upon the actual address value, which is 3 bits here, and this is binary, and 000 corresponds to the location 0. So that is being read and put into dout1 next, and so is the case for all other locations. It all depends upon what address we encounter, and note that only one address can come at a time. So it will be one of this that will be processed, not all of them, and that was for address 1, and there is also a default in order to cover don't cares or tri-state, and once again it is a dummy statement. At random I have allocated this. This is not going to come in the regular processing anyway, but yet we had to take care, and we started with a case, so we had to end case here, and we start one more case within the same always block, and this time we will have the address 2, and this is the reason why we are in a position to access 2 different datas, namely data out 1 and data out 2 simultaneously, because all these Verilog statements are in general concurrent, and naturally this case and that case will be concurrently, that is simultaneously processed, and it is exactly the same as the previous one. Location 0 is allocated now to dout2 instead of dout1, because this happens to be the address 2, and once again only one of these addresses will be processed at a time, and whatever be the address, and it will process that particular statement as such, and it will retrieve that particular location, and each of these locations is 64 bit in width, and once again we have a default and then an end case here, and we started with a begin at after always, so that is an end here. So, this is the first pipeline stage, and we need to use only positive edge clock. Note that no reset has been used here, and at positive edge of the clock we have already seen that we have retrieved it from the ROM table. This is the ROM table. We had two tables what we have already seen, and these are all the contents of the ROM. So, whatever is the address in address 1 or address 2, that will be retrieved, and that corresponding location will be retrieved. The data that is retrieved is precisely one of this, and assigned to this location 0 through 7 depending upon what address, depending upon the address that we give. And we have already mentioned that simultaneously you can supply two addresses and get two datas as such. The data what we get is 64 bit, which we have seen just now, and so this is the first pipeline that we have already seen, and we have just now seen two case statements, the output of which is this dout1 underscore next, and this is assigned to dout1 reg1. This is the first pipeline stage. So, earlier in the case what we have had is only a combination circuit and retrieving the ROM data, and that ROM data when a positive edge clock is encountered, it is assigned to dout reg1. So, this is once again an intermediate output, and this will take it as the input for the next clock edge. This is the second pipeline. So, note that what we assigned here to reg1, this is the actual ROM data, and we assigned here this 2 corresponds to 2 addresses. We want to simultaneously access 2 locations, that is the idea here, and this is assigned here at when the clock strikes, and positive edge of course. So, this is the final output that we have. So, dout1 and dout2 are the 2 data corresponding to the final output. So, we there is a begin, therefore, there is an end, and there is an end module here, and so this is what we had here. So, this was the ROM here with 2 addresses, and we wish to simultaneously retrieve 2 locations, and each of these location is 8 bytes in width, and this is the requirement for DCTQ design application. That is the reason why we went for an unconventional ROM implementation, which is possible on FPGA as well as ASIC, because number of chip area is not too much here in this case. If the chip area is increases of the order of several kilobytes, still you can accommodate in high capacity FPGAs, but there is a limit for all this, and even in ASIC you will have problem, because later on we will learn while designing dual RAM that there is a statement which invokes register arrays. It's a register is nothing but a flip flop. So, those are invoked. So, fundamentally they are all flip flops. So, there is a limit both in FPGA as well as ASIC design. In ASIC, however, there are specialized vendors who have ample design experience on custom built memories. Such vendors IP cores can be bought and integrated into your design if your design requires either the conventional RAM or ROM or tailor made custom built for your application. So, in FPGA we have this more limitation, because we can't go beyond several tens of kilobytes of memory, and so this fortunately is not much. 8 into 64 bits only are being used, and that is the reason why we have gone for this coding. And so, let us see the test bench now. So, the code is quite simple here. So, this is the test bench for testing this dual address ROM design, which we have just now covered, and once again we have a clock operating at 100 megahertz, that is why we put a 5 here, and this is a back annotated file, and the corresponding back annotated waveforms also you will be seeing shortly, and that is why we have included ROMC back annotated .v file, which is precisely the same as ROMC.v, except that this has been obtained after back annotation. And the test module is ROMC underscore test, that is why we have to declare it here, and herein what all we are interested is only the data outputs, and which is declared here, and inputs in test bench, as I mentioned, will have to be declared as registers reg, and now we invoke the design ROMC here, and module is still ROMC, even back annotator file, if you see open it out, you will see the very same module name which we have used in our design, and this is the instantiation. If you want to call many more times, you can just change this one, and once again port name we are using, and so that we can put it in any order, and these are all the inputs here, clock, and they are all synchronous ROM here, and 2 addresses are there and as inputs, and corresponding outputs manifest in DOUT1 and DOUT2 respectively, and being a test bench, we will have to take appropriate action with reference to time, and we can use the initial statement. There will be a begin and corresponding end will be there towards the end, and we need to initialize the clock, and here we have 2 addresses. So what we will do is we keep on changing at different points of time the addresses. To start with, address 1 and address 2 are initialized to different values. For example, this is 0 and this is 7th location. This corresponds to location 0 and this is location 7. That means to say, when we, suppose when you process this, you can access location 0 as well as location 7 simultaneously and get it at the outputs DOUT1 and DOUT2 respectively. That is the implication here, and this is deliberately done to different addresses are given here, so that you will get a feel of it when we see the waveform. And here I just staggered the address bit by 7 nanoseconds in order to avoid the very first clock, and first clock edge happens at 5 nanoseconds because 0 starts right at 0 time, and so I wanted to avoid first clock, and so that, and remember that we have 2 stage of pipelining. So that means to say the data can manifest only at the 3rd clock. So that is the implication there, and that is the reason why we have staggered a bit, so that clock there is an offset between the address change and between the clock edge. Clock edge occurs at 5 nanosecond, and we want to avoid that first clock, so we are delaying a bit here. That is the implication there, and every time you see here we apply 2 addresses, address 1 and address 2. One we will start with applying 0, then for address 2 7, and keep going. Every 10 nanoseconds we have a 100 megahertz operating frequency, so every 10 nanoseconds we keep changing the address, and corresponding data should manifest, which we can observe in the waveform. And here instead of binary, you can also use a decimal here, in which case you need to use D here, and say straight away use 0 1 2 3 and so on. And here you notice that all are incremented as far as address 1 is concerned by 1, 0 1 2 3 and so on, and whereas address 2 goes the other way, 7 6 5 and so on. This happens every 10 nanosecond, and finally when you are done, you stop, give some cushion and then stop here, and there was a begin, therefore there is an end, and as usual we need to toggle the clock. This is the standard statement we have been using all through, that is with the always statement here, and this data was 5, therefore 10 nanoseconds is a time period, therefore 100 megahertz. We started with a module for the test bench, therefore there must be an end module. And before we go into the synopsis results, let us have a look at the waveform for this here. So I will first explain this and then zoom, and here what we have is a clock here, and you can see the waveform of the clock, and address 1 is here and corresponding data out 1 is mentioned here, and address to, you have a question? Yes.
This is an interesting question. What if the same location is accessed by both the addresses?
There is no problem. As I mentioned, that can be the address can be very same thing, right. So, I have kept it deliberately different thing just to get a feel that different addresses are working. So, you can repeat the same exercise by using the very same address, right. So, and I have cross checked that also works fine, there is no problem, because the statements are very plain, Verilog statements are straight away case. So, there is one to one correspondence. And notice this one, as I mentioned, there is a clock here rising at 5 nanosecond, this is 20 nanosecond, therefore this 10, and when you this is midway here. So, this is 5 nanoseconds off time, then 5, so that is what the clock is 100 megahertz. So, it should amount to 10 nanoseconds, and we apply the address right here. Actually at 7 nanoseconds only we apply, and by default this simulator has I think clearing it does all by itself. So, that may be the reason why it is like that, but it is not really true, because 7 is also coming here, and this is little inexplicable, because we have given at 7 nanoseconds only, if you remember, right, the test bench. And let us see, no, 7 nanoseconds we are writing the same information once again. See, address 1, address 2, 0 and 7 are already done at 0 nanosecond, right. So, you have to take care, just always verify, cross check, then you will see what the reason is, and so that explains why it is 0 and 7 here. And actually we actually start only after 7 nanoseconds. So, and after 17 nanoseconds only, so the address will be changed, that is the meaning there, because as per the this one we are changing at 7, the cumulative time, if you take 7 plus 10, 17 nanoseconds only, we apply the second address here, and that is what is happening here. This address is happening here. So, you should not take this as the first clock, that is what I am trying to impress upon you. So, the first clock actually is this one, and second clock is this, and now let us see where the output is. D out 1 corresponds to the address 1, and as I mentioned, it is a 2-stage pipelining. So, it should manifest, the result must manifest only after the end of 2 clock pulses, not counting this first one. So, the first one happens here, then second here, then third one is going to occur here, but the data is stable right here. So, the corresponding data here is if you read here, it is 5B, all 5Bs here. So, let us see the table here. So, just remember 5B here, and similarly address 2 is 7, and corresponding data is what you see here as 19B9 and so on. So, it is precisely at this point of time, 37,000 picosecond is 37 nanosecond, right at this point of time where the cursor is. And here you just remember this, at least few numbers here, all 5Bs here, and 19B9, some 47E7, and let us see what we have given here. In the design, if you go, so this is the data that we have given. So, you remember 5B, 5B, etc., and other one was 19B9, isn't it, 47E7. So, location 7 is this one, location 0 is this one. So, I think that is what we have been looking at. So, D out 1 is corresponding to address 1, which is 0. So, 0 address data is received only after 2 clock pulses delay. So, because of the pipelining here, and so you are there are 2 crowded, so many hexadecimal 8 bytes are there. So, you can't obviously show all of them, therefore, I just clicked on the cursor, and that cursor data is being displayed here, which is adequate here. And note that already the address has gone quite ahead because of the pipelining, right. and remember this data is for 0 address, and so is the case for address 7, the data corresponding data is 19. That is what we had. This was the very first location there, location 0 content and location 7 content corresponding to the two addresses 0 and 7, and so this is corresponding to next few. Address 1 has advanced further. I have expanded this clock here little more, and what you see here is, and the cursor is at this position, so it is 7E, 6A and so on. It is precisely the same here, and this is corresponding to what address? This is little this was 5B, so that was the first location. So this location must correspond to the second one, that is address 1 here, and this was 7th location. Now this must correspond to 6. So if you can remember this, fine, 7E here, then 3.1 here. Let us see the contents here. 3.1 is here, 7 is here, right? 7E, then 3.1. So location 1 and 6. That's what you wanted. Is it? Are we right? So that's what we have. Let me zoom a bit so that you can see very clearly. So this is address 1, and of course address you cannot view because of the pipelining, and this is the data that you have there, and this is the first data and this is the second data. So location 1, this is corresponding to address 1. So you should have, this is the data. Notice that the data is changing at too many places, right? So hence the this is because in our design we have put so many intermediate stages. So you can probably attempt rewriting, redesigning whether to improve this, so that frequency operation can be jacked up or not. You can try. I am not assuring that better solution may emerge, but you can try. In fact, I did not try other means because the frequency was already met, and that is the reason why data is changing, and ultimately it will get stable here, and that will happen before the clock, positive edge of the clock. You can see that positive edge of the clock happens here. It is right on the brink, but still it is safe, right? And similarly the other data what we have seen, this is corresponding to location 6. So just remember 7E82 here, 31, 31. So 31, 31, 7E82, that is what we had. 7E corresponds to location 1. So we have not mixed it up, right? And so this is what we have seen. We will see one more waveform here, and I will zoom this. So once again we will look at D out 1 and D out 2. This data is 31, 31, which is the same, just overlapped, so that you can view, and next data is here. You see that this is the positive edge of the clock, so it is expanded. So here, so the next edge of the clock, at this edge this data was valid, and this edge this data. So we have two datas here. Let us see where it corresponds to in the round table. So one is this is 5B, all 5Bs, and this is 19, B9, etc. So 19, B9, etc. 5B. So it is addressing location 0 and location 7. So address 1 is location 7 now here, is that correct? And this has come down to location 0. So and because of the pipelining, these addresses are advanced, further advanced. So, do not view the addresses, just take the data along, and we have seen this as well. Okay. So, we will just look at the simplify results and what it has to show. Let us see. This is the test bench we have already covered. The synopsis results, you see that it is quite a high frequency of operation we have reported, and here, and we have mapped onto a device which we are probably going to use our DCT design on this same device. So, hereafter all the designs which pertain to only the DCTQ application, and such as arithmetic circuits and dual RAMs, etc., and we will use this very same device with the possibly highest speed available, and it is a 240 pin package, and it is a vertex C combination, and it reports different flip flops usage, how many, and input buffers, output buffers, all that, and finally it reports LUT of just 68 for this ROM application, and Xilinx place and routes reports, and these are all the slices, 4 input LUT is used here, and the 2 of interest will be around 2000 gates. It's a standardized 2 input NAND gate. So, it is a gate equivalent, this particular design for dual address, and in addition to that you need additional gates if you want JTAG compliant IOs. And here you see that the frequency of operation has come down after place and route here. So, but still it is good enough. But once again, as I mentioned, what counts is the total system speed, not merely the individual modules. It is only as an academic interest we are looking at these figures, and it also creates a ROMC.bit for downloading into a hardware. And next we will consider one more design. This appears to be a conventional design. This is also used in DCT quantization, and this is used as a quantization table. So, in quantization we need to carry out division, not multiplication ultimately after getting DCT, which is the transform, and but division can also be implemented as multiplication if you just invert the quantization value. So, what is stored in this ROM table is the inverse of quantization, and what is stored here is actually once again in 64 bits, but when we want to retrieve it, we want to retrieve 1 byte at a time, although it is 8 by 64 organization. So, we want to retrieve as in a byte oriented manner, and this is off from the conventional design, and that is why hence we need to write a code for that. And mind you, it is 64 bytes totally, each is 8 bytes. So, like that 8 locations, so 64 bytes totally. So, naturally it calls for an address of that size, 6 bits here, 2 to the power of 6 will give you so many location, and the design starts here. I will just read out the comments here. This ROM stores the inverse of quantization values, 8 bits unsigned. So, quantization value is it is an inverse of quantization value as I mentioned before, and although it is organized as 8 by 64 bits, it is byte addressed while reading. So, while reading only, that is byte addressed and retrieved as a byte and processed further, because for we need to divide a DCT value which will emerge at every clock pulse, and there are 64 coefficients in that, and each coefficient will have to be divided by this quantized value in order to get a quantized DCT, and that is what brings about compression, which we will see in greater depth later on when we talk of the design application. And here the design module is quantization. So, it is Q is annexed here for ROM. So, it is called ROM Q module, and it has 2 inputs, one address which we have already seen, as a width is 6 bits and its data is 8 bits here, and we declare the input outputs here, and this is a register we will be using in pipeline stage once again here also, and So, data will be in the always positive edge block, therefore, it is reg here, and we also need an intermediate assigned value which we will declare as wire here, and that is precisely same as D here. It is an intermediate value to store the data. And now as I mentioned, memory can be realized by as a flip flop array. So, you can just by one statement you can declare any size memory. For example, this has note with char here. So, it is declared as reg here, and you give the width here. So, if it is 64 bit, you want a memory which is 8 into 64. So, that 64 bit width is specified first, and you can declare, you can give a name for the memory. For example, I have given it as MEM. If you want call it as something else, say RAM or ROM or whatever, you can call any name, any meaningful name you can give for your memory. And these are all the locations. So, number of locations are 8. So, location 0 through location 7 we have tackled earlier in the same fashion, and this one is the highest order address. So, location 7. So, this is the nomenclature, even here first MSB, then followed by the LSB here. So, this is a typical memory realization. This is an important thing we should remember. For any memory realization you can use an array of this type. And similarly, one more array also has been used, and ROM is organized as 8 by 64 bits, and but read byte by byte, right. So, in order to assist bifurcating this word into bytes, we need one more here array here, and that is what is declared here. And in addition to this, we need some more signal. For example, memory data, this also is 64 bits, and there I mean it is a combinational output. So, we declare it as wire here. So, also we need location 0 through 7 as in the previous case, each of which is of the same bits, 64 bits, and they are all wire, and that is because we are going to use assign statement here. And as before, we have exactly the same, only difference is data is different here. So, these are all the inverse quantization values stored in the ROM table, and as I mentioned here, it is 8 number of locations, each is 64. So, the organization is 8 into 64. As far as the storing is concerned, this being a ROM, it is only storing device. So, while retrieving, we want to retrieve for we have 6 bit address. So, when we give address 0, we want to retrieve FF first. So, for address 1, we want to retrieve 80 and so on. For this 7, address 7, 3C will be retrieved, then 80 will be retrieved at 8 address, and so on. In a raster scan order, you can just address that. And finally, for 63 address in decimal, 19 will be used. When we see the waveform, we will come back to this and see. And once again, this is a combinational always block, and whenever that locations change, only then we need to take the do the processing. And what we are doing here is we have used reg mem array earlier, and so this is the way to retrieve a particular memory location. Those who are familiar about microprocessor and the RAM design will follow it very readily. So, when you say memory, the address you give here within the quotes. So, straight away that it will go to that location, take the 0 as the address and retrieve whatever is stored in that 0 location, and in fact it is the other way. It goes to the location 0 here because it is a ROM, we want to read from the ROM. Location 0 is nothing other than the data that we have already stored, that is retrieved as memory 0. So, this is done so that address can be varied later on. So, we will go into the details little later. So, what precisely it means, it will be clear when we deal with that later on. So, now the comment says here bytes from each row accessed in raster scan order must be first. We have already seen that FF was the first one, that is accessed first, and so this is the flexibility in writing Verilog code. So, suppose you are not happy with MSB first, you want some other thing to be retrieved first, you can always write a code to change to your particular custom design. So that is the beauty of Verilog coding here. And so we have one more always block, and this time another variable is used, memory data, and notice that memory data is byte access here. For example, 63 to 56, if you subtract this you get 7, so plus 1, so 8 bits totally. So in this order, lower order bits are assigned to different byte data 0 and so on. So this is only to facilitate change of 64 bit into 8 bit notation. So that is what we have here. So what here it will be plain. So we have used memory data earlier, and we have also used memory that within brackets the address. So here we can straight away define the address, this MSB of the address we had taken here 345, and that particular thing will fetch this memory data. Memory data is nothing other than what we have here. So it is clearly only a byte is being fetched here, memory data here, right, and that is fetched from the address pointing to the MSB of that, and LSB of the address will fetch the byte data. So this byte data then give the address. This is in fact this is the byte data here, and memory is what we have. So when we say memory data, so what it implies here, let us see, have a look. Actually we say memory data, it actually implies all the 64 bits, it does not mean this, right. This is there only to in fact reassigned as a byte data here. You are separating out a 64 bit content as a byte content here, right. Is it clear? In fact you can see memory data having declared earlier somewhere. Memory data, as I mentioned, this is actually 64 bit, and data byte is to get only 1 byte at a time, and that is what it is there, that is what we have seen here. So that is what these two statements are doing. So you retrieve the byte data, and first from the one complete 8 byte location as such, and this is single pipeline here, and this D next is nothing other than the actually retrieved byte data corresponding to address A, which is sum total of all the bits 5 through 0. From you have to see together these statements, then only it will become clear that it is address completely 0 through 5 address. So and which outcomes, the outcome will be 1 byte as such, that is what we have here, and this is this byte which we have read corresponding to A address is assigned to D here, and we end up this, and finally the module is also ended. So this is the test bench for testing the ROM, and as usual these are all the include statements, and this ROM queue test here. Here what we need is only a D output here, and we declare as output here being only 1 byte, and we need to have inputs declared as reg, so we have it here, and we instantiate the design, invoke the design and instantiate and port by name. And note the an interesting thing here, we are using one count as an integer we are declaring. This is exactly a C like structure, it is precisely the C program, exact counterpart of C program. I mentioned that in RTL coding we should avoid all this, but we are doing using this only in the test bench. So if you had you use this statement, for example for statement is used, which is precisely a C statement, and for count equal to 0 and for count less than 64. So every time you count advance the counter. So what we need to do is and assign this count to the address here, that is what this for loop is doing. This is exactly counterpart of C, and this is a violation of RTL guidelines, and you should not use this in the design. You can use in the test bench, because it gives a much concise coding. You can call it programming for the test bench, but it is a pseudo thing. We can sometimes we have also used RTL coding style here, although it is not really required. So, we can violate in the test bench, but not in the design. This should be very clearly borne in mind. I think I have been mentioning this right from my day 1 when we started the Verilog coding. And once having covered all these 64 addresses, we need to give a little more allowance and then stop here. And as usual, this clock is running at 100 megahertz with this statement, and there is an end module here, and the results are here. It is running at 123 megahertz here, and prior to this, let us have the waveform here. So, remember that there is 7 nanoseconds in test bench here also, as in the previous example. That is why address is applied from 7 nanoseconds here, and so there is a clock here. There is a this is the data out, and this count is also displayed here. So, you notice that it keeps on advancing. This is to facilitate supplying address here. In fact, this is same thing is being applied here, and this is synchronous and with one pipelining. So, the output comes delayed after this. You can see here. This is the clock which is responsible for this retrieving the data corresponding to 0 address, and the data is FF. You remember that we started with that earlier FF80. That is precisely what you have here. So, you can just zoom. So, you can see FF80 and so on, right. And notice that this is the clock which is responsible, but it comes only after gate delay because we are using a back annotation here, and FF806C and second waveform you can see here, they are all towards the end. This is 62, 63, 25, 1E, 19, etc. So, if you see the content here, you can see FF80 and last one 1E 19, you can see that. So, you can see 2D 25 1E 19. So, this is consequence. So, you can see this 25 to 18 19. So, this establishes the working of the design, and finally, we will have a look at these are all the simplified results we have seen here. It works at 123 megahertz and corresponding and we have used the very same device that we have mentioned before, and it has taken just 37 LUTs for this design. And place and route result is 319 gates here, and ROM Q dot bit is the output, and it operates at 152 megahertz. Okay, thank you.